Okay, in this presentation we are going to look at another Introduction to R for Actuarial Students example. This corresponds to the CS1B curriculum, which is essentially an introduction to R programming and the fundamentals of statistical analysis. Now this is question 1 from this particular paper. In a very small empirical study, a sample from a random variable x is observed. The data can be entered into R using the following code. So we have, I think, 18 values there, 18 observations from this random variable x. Okay, so the first question is estimate the expected value of x. Now that's straightforward enough. We actually just have it typed in x, so we just have to specify the command mean and the vector x, the mean of x, 0.5738. Okay, so that's straightforward enough. The second question is exercise 2, calculate a 95% confidence interval for the expected value of x, assuming that x is normally distributed. Now we'll talk about this shortly, this assumption. But just taking the question at face value, this is the command we would use. T-test x. We would also specify the confidence interval of 95% using that argument there, conf equals 0.95. So if we're asked for 99% or 90% confidence interval, we can adjust this argument accordingly. So this is the output here, a one sample t-test. The key thing here that we are looking for is the confidence interval. So it is 0.427 to 0.720. Okay, just allowing for couple of decimal places. We were also given the mean here, again 0.5738, and we're given a t-test output. So this corresponds to a hypothesis test, the one sample test. This is the name of the data, the test statistic, the degrees of freedom, the p-value, and a statement of what the alternative hypothesis is, with the null hypothesis being equal, or not equal to, the exact opposite of this statement here, which means true mean is equal to 0. That's the hypothesis test being sought here. Now that just doesn't really make sense in the context of what we're doing. All we're really asking for is this confidence interval here. So that's all we'll do. Now, we're assuming that it is normally distributed, but let's test this out a bit. So let's just go a little bit further with this. We're not asked this in the question, but we'll just sort of see what we can do here. So something we can use is the Shapiro-Wilk test, and the command for that is shapiro.test, and just specify the name of the vector that you're testing. This brings up an output. The Shapiro-Wilk normality test, it just gives the data x, which we have created. This is the test statistic here, which we don't really look at, but this is the p-value here that we will judge. The null hypothesis is that the data set is a sample drawn from a normally distributed population. The alternative hypothesis is that it is not. It's drawn from a population that is not normally distributed. So in this case, we reject the null hypothesis. We would sort of go along with the conclusion that this data set is not a sample from a normally distributed population. Basically, it's not normally distributed. So we can check this against a QQ plot. So this is how we would test it here. I just added in some code just to make it a little bit more legible. So the QQ norm, X, and these are some specifications just to make it a little bit more legible. Also, this just actually sets out the quantiles. This sets out the quantiles, the scatter plots, points. The QQ line sets up a trend line to help us gauge the plot. So if the points are following this trend line, then we would say that then we would assume that the data set is normally distributed. But in this case, that's not the case. Anyway, we can also use the tidyverse package, Magritte and Broom specifically. So this is using the output we've created previously, and what we could do here using this command tidy is to sort of set up a very tidy looking data frame that we can look at and check our answers from. So the confidence interval here is conf high and conf low. So, and those are the values there. And so this is just a sort of compacting the output that we've previously seen from that test. Now, the next thing is exercise 3. Construct a confidence interval for the expected value of x using a bootstrap method with 10,000 bootstraps. Okay, so just going to sort of demonstrate a couple of things here. So I have some, I actually just sort of went a little bit overboard with this, but I have some sequences here: 1 to 4, 1 to 5, and 1 to 6. Okay, so they just give you the values 1 to 4, 1 to 5, and 1 to 6. The integers stepped up in units of 1. So here is the sample command, and here we have the 1 to 4. So this is just the set of values 1 to 4, and we're going to pick 3 values from that. Replace equals true means that if a value gets picked, it can get picked again. So here, just pick out 3 values between 1 and 4, 1, 2, 3. 3 values between 1 and 5, 2, 3, 5. And here, 3 values between 1 and 6. And again, a value can be picked twice. So 5, 3, 3. Okay, that's replace equals true. Now, suppose we don't specify the number of items that we want to sample from, or from whatever we're sampling from. Sample here 1 to 4, replace equals true. That means we will pick out 4 items because this has length 4, this has length 5, 1 to 5. So we pick out 5 items, 1, 2, 3, 1, 4, 2, and likewise 6. Sample size is 6 here from our, we're sampling from 1 to 6, okay, because we don't specify the number of items. So X has 18 items, if you recall. I think it has 18. So what we're going to do is from X select 18 numbers, okay, and a number can get selected again, okay, and then we get the mean of that, okay, that sample, and there's a couple of values, a couple of sort of possible values there when we run it 5 times. Replicate means that we repeat an operation a specified number of times. Here we're going to specify it 5 times, and we're going to repeat this operation 5 times and collect the results here. Okay, so this is 5 means from 5 samples drawn from X. Okay, and what we can do is build up a population of that. This is actually just more examples of the same thing as well. Just put in 3 just to fill up the page basically. So what we can do is run that 10,000 times, okay, replicate that 10,000 times, and then save that as Y, and what we're going to do there is get the quantiles of Y for the probability of 2.5% and 97.5%, 0.025 and 0.975. So this gives a 95% bootstrap confidence interval, 0.45 to 0.719. Okay, let's just go back a bit and just compare that to, this one here. It's not too far off actually. Anyway, we'll continue on. Comment on the differences between the confidence intervals in exercises 2 and 3. They're actually very similar. The CIs, the confidence intervals, are almost identical, but with the confidence intervals in exercise 3 being narrower. The reason might be that the distribution of X is not normally distributed, and therefore the distribution of the mean is not normal for the small sample size that we have in this question. The bootstrap method provides a good approximation of the distribution of the mean independently of the type of distribution. So, that's a sort of a good counterpoint to the conventional t-test confidence interval there, just to sort of, what happens when your assumptions break down, like for example the assumption of normality. Okay, we'll leave it there.